cross-sectional area of the rocket was 0.00881 meters per second, or meters squared. We assumed that there would be no wind throughout the whole simulation. We assumed that the drag coefficient would be 0.5 because we found a nose cone and that was the drag coefficient of it. And we assumed that the mass of rocket would be 6.6, but it wouldn't be that the whole way. Or we found that by looking at online to find different like nose cones and body tubes and stuff that would fit the engine that we decided to use. And we got approximately 6.6 kilograms when the engine is full, but the propellant shoots out over time. So we added into the XL the propellant shooting out. So the engine we decided to use was the Hypertech L550. It has a diameter of 0.0075 meters. The propellant weighed about 1.552 kilograms, and the total weight of the engine was 3.898 kilograms. So air density, we didn't want to keep it the same throughout the whole flight because that wouldn't be accurate. So we decided that we would look up a chart on digitaldutch.com for every 50 meters, and it gave us the air density, and we implemented this into our simulation, so it would automatically change the air density based on the altitude. So we also wanted to make this as accurate as possible, so we used the thrust curve instead of just an average thrust throughout the whole time. So the burnout is approximately 6.3 seconds, and that graph shows the thrust versus time.
So this is the equation we used in Excel for the force of drag. It's the half of the drag coefficient times the area times air density times velocity squared. So this is a graph of drag over time, and so you'll see that as our engine accelerates us, our drag increases because our velocity is increasing, and so we're creating more drag. And it starts cutting out briefly before burnout because the engine is decreasing on acceleration. And then at apogee, you'll see it starts to increase. It's going negative, of course, because we're going down, but it is still increasing in value. This is the equation we use for net force, which is the force of the thrust minus the force of the drag, minus weight, basically, which is mass times gravity. Net force, you'll see the thrust, the engine is acting on the rocket, and so it increases at an exponential rate very, very quickly. And this, along with acceleration, which I'll show in a second, basically model the thrust curve, but subdued by the amount of mass that our rocket is carrying. So it's basically just the thrust curve in the simulation. And then that force increases drastically at burnout, decreases because there's no longer an engine acting on it. And then at apogee, it starts to increase in value again. This is our acceleration formula. It's the net force divided by mass. And like I said, this is the, if you look at it, and on the next slide it will expand, but you'll see that it is the thrust curve, just subdued by the amount of mass that we have over time. So if you'd like to switch to the next one, you'll see that as we expand, it's just the thrust curve that we use, but kind of subdued by the amount of mass and the rest of the variables that we threw in due to gravity pulling down on it. So this is the burnout is due to it decreasing after burnout is obviously due to gravity because there's gravity on our planet, so that would make sense.
So the formula for velocity that we used is the initial velocity plus acceleration times the change in time, and our change in time was 0.1 seconds. So for the velocity, as the graph shows velocity in meters per second versus time in seconds, and apogee and burnout are labeled on there. Apogee is 23.6 seconds and burnout is 6.3 seconds. And the max velocity happens at 4.4 seconds and is 343.2 meters per second. So the formula for altitude that we use is initial altitude plus velocity times the change in time plus 1/2 times acceleration times the change in time squared. And so burnout and apogee are also labeled on this graph, and apogee happens at 23.6 seconds, which I previously stated, and the apogee is about 3,690 meters, which stays under the 13,000 feet maximum. So the speed of sound, this is a chart from digitaldutch.com. It shows the speed of sound for certain altitudes because the speed of sound gets lower when air density gets lower. So we wanted to make sure we crossed it at the different altitudes, so we wanted to be more specific. So we did break the sound barrier. It happens at about 4.1 seconds, and we drop below the sound barrier at 5 seconds. So this is the graph of the Mach speed that we go. As you can see, it goes above 1 it goes above 1 over there, and the highest speed is at 4.4 seconds, and we go Mach 1.02.
So this is a feedback diagram showing forces acting on our rockets at 0 seconds right before we launch. We still have the total weight of 6.6 kilograms because we have not lost any fuel yet, and the net force is 0 because the normal force and gravity are balancing each other out. So this is about the time we lost all our fuel at burnout, so our rocket's going to be about 5 kilograms. The net force is negative 221.6 newtons because of the drag and gravity acting upon it. So at 23.6 seconds is when we hit apogee. There is a slow less force, so it's negative 49.2 newtons. We're still at the weight of 5 kilograms. There is little drag to no drag at this point, so. And so this is about when we are landing. We currently do not have a parachute factored into this, so we are hitting very fast. About 8.1 seconds with our drag at like 51.5 newtons, and our net force is close to 0 because we are about to hit the ground, so it's 2.27 newtons.
Okay, so we kind of look back at our Excel spreadsheet and our profile and kind of ask ourselves, well, did it work? Like, did we get the expectation? Did our expectations like actually meet reality? And well, yes, most of the graphs that we got and like the numbers we got back were realistic and they made sense with what we had put in as variables and just factors. But of course, we still needed to work on parachute because we don't want a rocket landing at however about
350 miles per hour.
Yeah, that would not be a fun time to clean up for anyone. So we need to factor in a parachute, and so, you know, obviously earlier he was talking about how it happens over a couple of seconds, so we're thinking about doing that as well. Any questions?
Well done.
Very well done.
Have you guys thought at all about, like, you've gathered all these different inputs, and you're kind of taking them at face value. What if you're wrong a little bit? What if that thrust curve is a little bit less than they tell you? What if the drag is a little bit more? That's something you can play around with. So I noticed your Mach is 1.02.
Right.
That's really close. That might be something you could look at is how sensitive are you to some of those inputs? Is there anything you might want to do to have a little bit more, we would call that margin, where maybe you'll shoot past Mach 1 a little bit, but that way if you're wrong, you're going to make sure you get past Mach 1.
So
Does that make sense?
Yeah, we were thinking about changing the amount of mass on a rocket. So we kind of went a little high with the amount that our tubes weighed and stuff like that. We kind of changed them a little bit as we went on. We realized we overweight how much they actually were. But the tubes are a little bit on the heavier side, and there are a couple of things we could do to kind of adjust how our rocket would fly, including like our drag coefficient, stuff like that. We get a better nose cone because it's an average. It's not like it's an average nose cone. It's not necessarily like the best nose cone we could find. So there are a couple of factors we play with on the actual body of our rocket once we get to designing it.